Hello everybody, this is Muhammad N. Murshid. I'm from the Department of Mathematics here at UTC. The topic of my project is in search of the time-dependent operator in the dynamic mode decomposition. Let's begin. Here is an outline. At first, I will go over the motivation behind this project, and then would come the background, which would be on dynamic mode decomposition, DMD in short form. Afterwards, I will cover the new findings, which is essentially the analysis related to time-dependent operator-based DMD and observable space-based DMD. Then I will present the numerical results. Finally, we will draw some conclusions, and there will be some references at the end. So there's data all around us, and we are constantly looking for models that can capture the dynamics in the data. Basically, we want to extract knowledge from this data. Dynamic mode decomposition is a data-driven technique that can create a model from time series data. It works well on low rank data, linear data, but needs to be updated to handle data containing non-linearities. We do an analysis to evaluate the effectiveness of a time-dependent operator in DMD and explore DMD in observable space. Here is the background on dynamic mode decomposition. First introduced in 2008 by Schmidt and Sisterhan, dynamic mode decomposition generates a model from spatiotemporal data. Let's consider that we have some data in the form of a matrix, capital X sub 1 to n. So this matrix is made up of several different column vectors. Each column vector is the state vector at a particular time instant. So initially this column vector is the state vector, and after some time, after some time step dt, we have the state vector x2. So x2 is the column vector that would give the states at t2. So we have up to xn. DMD at first splits the data, this data matrix, into two parts, x1 to n minus 1 and x2 to n. So x1 to n minus 1 is defined this way, and x2 to n is defined this way. Okay. A mapping matrix is computed to relate these two matrices. So it's more like we seek a matrix that can be multiplied by this first part so that we get this second part. Singular value decomposition of the first part will be required to form the low rank mapping matrix. An eigendecomposition of that mapping matrix would result in the eigenvalues and eigenvectors, which would help us construct the dynamic modes. The routine for DMD is provided on the next slide. So here is the algorithm uh, of DMD. So we need to input the data sequence, which will be split into two parts. And then we do the SVD of the first part, and we try to find the lower rank version of the mapping matrix S tilde. And then we do eigendecomposition of that mapping matrix this way. And we use eigenvectors and all that to find dynamic modes, eigenvalues, um, and the future states are given by this formula at the bottom. So xdmd at time t is equal to this. So this formula can be used to reconstruct the training data as well as predict the test data. Time-dependent operator-based DMD. So we have already noticed that in the standard DMD, the mapping matrix stays constant. However, if we want, we can make that mapping matrix or operator time dependent. So in this new variant of DMD, the goal is to see if we can update the mapping matrix as we predict states in future. That is to say that the predicted state vector will be used as part of the training data to find the new mapping matrix. Given x1 to n minus 1 and x2 to n, we shall find S1 using this equation. The state vector in the next time instant will be predicted as per the standard DMD. This means we have a new column of data, and addition of this new column into the available data will result in the dataset x1 to n plus 1. So we had x1 to n, but now after one prediction we have x1 up to n plus 1, x1 up to n plus 1. Next, we will attempt to find a new mapping matrix based on x2 to n and x3 to n plus 1 via this equation. Okay. So this is how the time-dependent operator-based DMD works. Also, the mapping matrix can be expressed as a linear combination of the previously found mapping matrices. For example, we can use S1 and S2. We can take a linear combination in this manner to find a new mapping matrix, S3. And alpha and beta are some weights. This version of time-dependent operator-based DMD is also called the weighted operator DMD. So we're trying to weigh the already found mapping matrices in order to come up with a new mapping matrix. Now I will go over the observable space-based DMD. Observable space-based DMD uses nonlinear functions of the data besides the given data to see if it can capture the dynamics well. For example, we can consider uh, a data set, actually an extended data set, where we have the original data, x, and then we have x to the 1/2 as well as x to the 2. So we're trying to vertically extend the data set by taking into account uh, nonlinear functions of the original data. So capital X is the original data, and as you can see, we are trying to use nonlinear functions of that original data set. So these nonlinear functions of data are known as the observables. We can define the observable to be the original data and nonlinear functions of the original data vertically stacked together. So, and we will label this extended data set by G. So for capital X, it's G sub capital X, and for the shifted data, capital Y, the observable will be called G sub capital Y. Okay, so this is how DMD uh, is thought about in the observable space. Next, we will present the numerical results. Example 1 is based on the Burger's equation. Burger's equation is it's a nonlinear PDE, ut plus u sub x equals nu u sub xx, where u is some sort of signal that is a function of space x and time t. X is between 0.5 and 2 pi, and t in this domain where capital T equals 1. The initial condition is a Gaussian wave, as you can see, and nu is the coefficient of viscosity, and it is set to 0.1. This figure shows the signal u across the space at different time instants. So t equals 0, 0.02, 0.04, and 0.06. So the curves do show the behavior of u across space over time. So this is the dataset for example 1, and now we will test the standard DMD and other variants of DMD on this data set. This data in example 1. So standard DMD, here we show the actual signal at t equals 0.92 and the predicted signal at the same time. We see that standard DMD does well in capturing the dynamics. The predicted signal agrees pretty well with the actual signal. The predicted signal agrees pretty well with the actual signal at t equals 0.92. This is the eigenspectrum, and this figure shows the error um, versus time, and the error epsilon is computed by this formula. We take the 2 norm of the difference between the DMD approximation and the actual solution at a particular time instant, and then divide by the 2 norm of the actual uh, actual signal at that particular time. So that's the performance of standard DMD. And now we see how time-dependent operator-based DMD would perform. We see that uh, time-dependent operator-based DMD is it is okay, but it is not the predicted signal. In this case, is not as good as the one we saw in standard DMD. This is the eigenspectrum, and that's the error changing with time. So time-dependent operator-based DMD lacks eigenvalues with negative real parts. We see that from the eigenspectrum, we can see that um, there are not that many negative real parts compared to what we saw here. And that can be uh, that is actually related to how good the model is, or how good the model will perform. The prediction error is also higher than those seen by standard DMD. So based on this plot, we see that the prediction error is a little higher than those seen by standard DMD. The weighted operator DMD, we set alpha to 0.95 and beta to 0.05, and we notice that it improves the quality of the predicted signal to some degree, as we can see. So weighted operator DMD does a little better compared to time-dependent operator-based DMD. And we can also see the occurrence of some negative real parts in the eigenvalues. And the error is it's rising as usual, but um, it's kind of doing better than time-dependent operator-based DMD. Okay, here is the observable space DMD on example 1. We consider this observable H1 where we use the original data U as well as this product U sub x. Since as per the Burger's equation, ut can be expressed as a functional that consists of the term ux. That is the reason we have used such term. Here we plot the error versus time. The error in the testing set is the same for both the standard DMD and the observable space DMD. However, in the case of training set, um, the latter sees a sharp drop in its prediction error, whereas the former exhibits an increase in the error before this plunge. Next, we move to example 2. Example 2 is related to double gyre, which is a phenomenon where two counter-rotating vortices expand and contract periodically. Here are some relevant equations that are used um, to model the dynamics of double gyre. Um, the spatial derivatives of the stream functions. So psi is the stream function, and spatial derivatives of the stream functions on the domain this uh, result in the horizontal and vertical velocity as uh, as these. So u and v. That's how we actually find u and v, the horizontal and vertical velocity. And a is 0.1 omega 2 pi by 10 and epsilon is 0.25. The spatial derivatives of the velocities will then yield the vorticity as v equals partial v, partial x minus partial u, partial y. Here we can see the dynamics of double gyre. Initially, we have this two counter-rotating vortices, and over time we see that okay, the one on the left is expanding, and after some more time we'll see that it's contracting. Then we apply standard DMD and other variants and compare the performance. On this slide, we compare standard DMD against time-dependent operator-based DMD. From the plot, we can see that the prediction error in the test set for time-dependent operator-based DMD is higher than that of the standard DMD. So here, the red curve shows the error for the standard DMD, which is actually lower than what we see for the time-dependent operator-based DMD, which is shown in blue curve. Using a weighted operator DMD with coefficients similar to the ones used in example 1 yield no further improvement compared to the time-dependent operator-based DMD with no weighting. Now we try to use DMD in observable space. We take into account three different sets of observables. The first one is just the original data phi. The second one is phi plus phi sub t, that is the time derivative of the original data. And in the third set, we have phi as well as exponential of the negative of v squared. From this plot, we see that the behavior of the prediction error for G0 and G1 appear to be the same for both the train and test set. In contrast, the prediction error for G2 goes down by a few orders in the training set and is marginally lower compared to that of G0 and G1 in the test set. Okay. To summarize, the time-dependent operator-based DMD with well-chosen weightings can produce good predictions over the time-dependent operator-based DMD with no weightings at all. However, this is not the case all the time. The standard DMD is still superior to the time-dependent operator-based DMD. The use of observables can lead to a speedy decrease in the prediction error in the training set. The observable can be a part of the functional that makes up UT or standard functions like exponential, sine, cosine, etc. In future, we plan to create a library of observables that can be helpful not just for data derived from PTEs, but also on those that are completely drawn via lab measurements or sensors and where which are not much which are not actually physics informed. And also we want to test the different variants of DMD on a different data set, different data sets, probably in higher dimensions. Okay, so that was the summary and our plan for future work. Big thanks to Dr. Hong Chin for allowing me to work on this topic as part of a project in the course CPSC 5240. Here are some useful references. Actually, there were many good references, but I've just put here some of the useful ones. I would like to thank you all for listening to this talk on dynamic mode decomposition and actually this was an analysis on how we can look for the time dependent operator in DMD and also how we can like what are the prospects in finding the dynamics as we explore the observable space. So yeah, this was an analysis and we tried to test new things out and we did our best to share our results with you. So thank you again for listening to this talk. Yeah, thank you.